Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on linear algebra, chapter algebraic multiplicity and geometric multiplicity, lecture number 1, in which I will give the concept of algebraic multiplicity and geometric multiplicity of a characteristic root of a matrix. Now I will give you the concept of algebraic multiplicity of a characteristic root of a matrix. Let A be a square matrix of size n by n, and let lambda I be one of the characteristic roots of order k, then k is called the algebraic multiplicity of the characteristic root. Lambda I of the matrix A. Here we see that there may be many characteristic roots of square matrix A, and we have assumed that lambda I be one of these characteristic roots of the matrix A. If lambda I means characteristic root lambda I is repeated k times, then k is called the algebraic multiplicity of the characteristic root lambda I of the matrix A. By an example, I would like to clear this concept. Example. Let A is a 3 by 3 matrix whose elements are 4, 1, 0, 0, 4, 1, 0, 0, 4. Let this is a matrix. Let lambda is a characteristic root of matrix A. Therefore, the characteristic equation will be A minus lambda unit matrix I determinant equal to 0. Let this is number 1, this is number 2. Implies that A is a matrix 4, 1, 0, 0, 4, 1, 0, 0, 4. This is matrix A minus lambda unit matrix I 1, 0, 0, 0, 1, 0, 0, 0, 1, and its determinant equal to 0. Implies that 4, 1, 0, 0, 4, 1, 0, 0, 4 matrix A minus, we multiply this matrix with lambda, lambda 0 0 0 lambda 0 0 0 lambda. Determinant equal to 0 implies that 4 minus lambda 1 minus 0 1 0 minus 0 0 0 minus 0 0 4 minus lambda 1 minus 0 1. Here 0 minus 0 0 0 minus 0 0 4 minus lambda. Determinant equal to 0 implies that if we take this determinant, we get 4 minus lambda whole cube equal to 0. Implies that lambda equal to 4 comma 4 comma 4. Therefore, the characteristic root lambda equal to 4 appears thrice. Therefore, order of the characteristic root lambda equal to 4 is 3. That means lambda is repeated thrice. Hence, the algebraic multiplicity of the characteristic root lambda equal to 4 is 3. Next example. Let matrix A equal to a 3 by 3 matrix whose elements are 6, minus 2, 2, minus 2, 3, minus 1, 2, minus 1, 3. Let lambda equal to characteristic root of A. Therefore, the characteristic equation will be determinant of A minus lambda I equal to 0 implies that determinant of 6 minus lambda minus 2 2 minus 2 3 minus lambda minus 1 2 minus 1 3 minus lambda equal to 0. If we find the value of lambda, we will get lambda equal to 2 comma 2 comma 8. Here we see that the characteristic root lambda equal to 2 appears twice. Therefore, algebraic multiplicity of the characteristic root lambda equal to 2 is 2, as it repeats twice. Here we see that the characteristic root 8 appears 1. So algebraic multiplicity of characteristic root lambda equal to 8 is 1. Now I will give you the concept of geometric multiplicity of a characteristic root of a matrix. Let A be a square matrix of size n by n, and let lambda I be one of the characteristic roots of matrix A if corresponding to the characteristic root lambda I of matrix A we get m number of eigenvectors, then m is called the geometric multiplicity of the characteristic root lambda I of the matrix A. By an example, I would like to clarify you this concept. Example. Let A is a 3 by 3 matrix. Elements are 4, 1, 0, 0, 4, 1, 0, 0, 4. The characteristic equation of A will be determinant of A minus lambda I equal to 0 implies that 4 minus lambda 1 0 0 4 minus lambda 1 0 0 4 minus lambda determinant equal to 0 implies that 4 minus lambda whole cube equal to 0 implies that lambda equal to 4 comma 4 comma 4. Let this is number 1, this is number 2. Putting lambda equal to 4 in the equation A minus lambda I x equal to 0 matrix, where x is a column matrix x1, x2, x3 and 0 matrix is 0, 0, 0 column matrix, implies that 4 minus lambda 1 0 0 4 minus lambda 1 0 0 4 minus lambda a minus lambda equal to this, and x is x1 x2 x3, and 0 matrix is 0 0 0, implies that putting lambda equal to 4, here 0 1 0 0 0 1 0 0 0, x1 x2 x3, 0 0 0, putting lambda equal to 4. Let this is number 3. Since number of non-zero rows of the coefficient matrix equal to 2, here number of non-zero row is 1 2 and this is 0 row. Therefore, rank of the coefficient matrix equal to 2. Therefore, number of linearly independent solution will be number of unknowns minus rank of the coefficient matrix. This is equal to number of unknowns with 3, x1, x2, x3, 3 minus 2 equal to 1. Therefore, number of linearly independent eigenvector equal to 1. This is number 4. From 3, we get here, we multiply first row, first column, 0 multiply x1 plus 1 multiply x2 plus 0 multiply x3 equal to 0. Now we multiply second row, first column, 0 multiply x1 plus 0 multiply x2 plus 1 multiply x3 equal to 0. This implies that x2 equal to 0. This implies that x3 equal to 0. Let x1 equal to 1, then capital X will be 1 0 0. This is linearly independent eigenvector. Therefore, number of linearly independent eigenvector corresponding to eigenvalue lambda equal to 4 is 1. Therefore, geometric multiplicity of the characteristic root lambda equal to 4 is 1. We have seen that the value of lambda equal to 4 appears thrice. So, algebraic multiplicity of the characteristic root lambda equal to 4 is 3. But corresponding to lambda equal to 4, characteristic root lambda equal to 4, we get only one number of linearly independent eigenvector. So, geometric multiplicity of the characteristic root lambda equal to 4 is 1. In nutshell, if the characteristic root lambda I appears k times, then algebraic multiplicity of the characteristic root lambda I is k, and corresponding to the characteristic root lambda I, we get m number of linearly independent eigenvectors. Then m will be the geometric multiplicity of the particular characteristic root lambda I. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button, and if you have not yet subscribed my YouTube channel, then please subscribe my YouTube channel. Thank you.